My name is Nick Barry. I'm the technical director of PlasmaBound, as I hope you'd guess at this stage. Essentially, what I want to learn you guys to understand from today is two things. First of all, that the idea of surface pretreatment is very important. It's actually a very, very important stage within your choice of materials on your material selection. Sometimes you can choose easy materials to work with, and sometimes you can choose harder ones, and there's a give and take in that process. The second thing I'd like you to learn is it is a science. It's not necessarily just a let's see if it works or not. And I'm going to demonstrate that today. And seeing as I see my commercial director down there, the third thing I also would like you to learn is that PlasmaBound has a solution for a lot of this as well, of course. So just to give you an agenda of today's presentation, I'm going to give you an introduction to the company that I represent here today, and then composite joinings in general, what's the purpose, what's the means, what does it do, joining problems that we see from a very, very broad perspective. And then we're going to move into PlasmaBound, its specific solution, and a summary of what we've discussed today. So essentially, just to try and introduce the company, PlasmaBound, we're based in Dublin, Ireland, within the European Union. And we are a spin-out of the University College Dublin and also the Centre of Excellence for Composite Processing within Ireland. So we have a good heritage. We have 13 employees in total at the moment and growing, recently closing another funding round and also closing a competitive round for funding within our global system. And we've had a total of private investment of 4.2 million, which is just to show that there is promise behind the technology that we show and use. And then also we're research-centered. That means that the technical director, which is myself, I come from an academic background with a desire to use the knowledge that I have to commercialize or to develop commercial solutions. And so I focus on taking what is known within university environments, and I bring it out to the non-academic environments or the commercial environments. So, into the meat of it all. Composites and composite joining, what is it? Well, traditionally, it is just the bringing together of two items. So you simply bring them, you join them. This can be for conductive benefits, and by conductive I mean thermal or electrical, and it can also be from the mechanical, which is traditionally what we discuss when we say joining. When we're discussing mechanical systems, I'm going to specifically talk about the mechanicals today. We would talk about bolts, rivets, things that put two items together, they compress them together. Usually there might be an adhesive in there to try and fixate the pressures and stresses. And this would be a very traditional means. Then we have bonding, which is this adhesive alone bonding, taking two composite materials or an alternative material and bonding that to composite. And then the third is thermal welding, which is associated with thermoplastics. And it's an area of interest for a number of industries, aerospace and the automotive manufacturers. The main core area that we're going to focus on today is the bonding, obviously, because that's where I see the future. Between welding and bonding are the two opportunities I see within the industries, particularly composite industries. So, the problem, as I said, and I promised, I'll try and keep this as high level as possible. It's recalls. Essentially, you've got your Model X, which in 2020 had 9,000 recalls for a simple problem, the bonding. The adhesive wasn't suitable. So they used an adhesive. It wasn't the right adhesive. And I didn't want to lament ye with a number of other recalls that have occurred, but just to highlight the point that Tesla aren't the only ones recalling. They're not the only companies that have these issues. They are a very, very front and prominent company, so they feature a lot whenever they have these recalls. And in fact, they are the most recalled vehicle despite having only 4 vehicles types. They are the most recalled vehicle in the world. But not all of these are adhesive related, but a good portion are. And that's where this presentation is trying to go. What I want you to see, if I do my job well today, is that when you're choosing materials, you have to consider the traditional 3 locations. Your adherent 1, which is your top surface, your adhesive, and then your adherent 2. What PlasmaBound look at, and other surface engineers will look at, is what's called the common interface. So we would refer to everything else as the bulk, and those material areas are the common interface. And they're key, and I'll explain why. Based on the ISO 10365, which we would all use for failure modes and defining what the failure is, essentially the first 2 areas here are in the adherent and the adhesive, and they're passes. They're good failures. The ones that cause recalls, they're the ones that occur on the common boundaries. It's where the adhesive hasn't done its job and it's not bonded to the substrate or the adherent. So that's the area we particularly focus in on PlasmaBound. So what do? We look at the surface free energy. To explain surface free energy, it's essentially just material or work, the work available on the surface of a material. And what type of work? Well, that's work that's associated with liquids. If a liquid comes in contact with it, how will it respond? And what that tells us, if a liquid responds in one way or another, it tells us how much energy is available on that interface to interact with other materials that come in contact with it. And you'll probably guess where this is going. An adhesive is one of those materials in a bond joint system. So we're using liquids, usually water and diodymethane, to do this assessment to find out how an adhesive will respond to the surface. So it's like a pre-test. We would use this system, it's probably the core use within our industry and within our company as well. We have 2 of these devices operating all of the time within the field. The main thing everybody will notice from this is hydrophobic systems. They tend to be low energy. Hydrophilic systems tend to be high energy. And so we associate them that way, and that's why water contact angle is often used in place of surface-free energy and methodologies. The distinction between water contact angle and surface-free energy is that it follows the OWRK, or Own, Rent, Rabel, and Kabul method. Again, I'm not going to dive into the science here, but essentially that splits it out into 2, dispersive and polar, which you'll see in blue and orange at the bottom line there. The blue and orange, the purpose of that is throughout the presentation, I'm going to maintain that color scheme. But the main point being you need 2 liquids for this, and as I mentioned them, water and diodymethane. So let's explain it very, very quickly and hopefully in a way that is illustrative. If we take it as a surface-free energy is like a handshake, it's the work that the surface is willing to do to a material. We take any surface, it's been handled by someone, so now it's contaminated. So now some of those the work that could be done is now already interfered with, and so it's not going to do much work or fold up the fist. And what we are going to essentially discuss here is that this surface has a combination of both dispersive energy and polar. And I have put the icons on the bottom here. Dispersive is like what causes a gecko to be able to stick to stuff. It's a lot of surface area, and it's called intermolecular molecular interactions. And then the polar is like the energy available within an imbalanced molecule, like water, for instance, where the fact that the ionic charge isn't there and it's imbalanced means that it is attracted to other materials by its heritage. So we have those energies available on the surface, and we interact with an adhesive that has this amount of energy needing to break it down. What happens? The contaminant will get in the way, where we had energy that could have done work, no longer will do work. But also, we are mismatching in energies. So we will end up with a poor bond. There will only be 3 forms of agreement. Of course, this is for illustrative purposes, but the point being, if you don't pick the right adhesive for the right interface, you will end up with a poor bond. It is a guarantee, and there is a science behind that method. When we look at that, how do you pick the adhesive? We can use things called surface or wettability envelopes, which come from the surface-free energy, and also surface tension, which is the energy required to break down the adhesive. So if we take, for instance, the concept here is essentially you have a virgin surface. It has this envelope being anything inside it is workable, anything outside of it is unworkable. So if we have an adhesive inside this envelope, which is generated by the surface-free energy data, if we have an adhesive inside this envelope, it works. If we have an adhesive outside of it, it does not. If we treat that surface, we suddenly increase that envelope. That means more adhesives will work with it. And that also means you can use cheaper adhesives, or more appropriate adhesives, or more technical adhesives, ones that can be conductive and still do the job that you want it to do. And this is why I'm saying it isn't a guessing game, it's a science. There is a reason you choose what you choose. So if we look at the surface that we would traditionally take, and we use traditional plasma, the weak polymeric interface here is still remnant when you do the treatment. So, and I'll explain what that really means, but ultimately what I'm discussing, or should use the laser for this, I guess. what I'm discussing here is this area here between the fiber and the polymer. It's not as strong as the fiber system because it's just pure polymer. And the reason why we put fibers into composites is to reinforce them. So when you do traditional plasma, you will have the remnant of this weak polymer layer, and you're difficult to remove contaminants. But if you have removed the contaminants beforehand, traditional plasma is very good at increasing the energies and causing adhesion. Now, I'll explain why I'm using the term traditional plasma in a minute. So when you look at abrasion, which is hand sanding, causes a disruption, you get fiber interruption. What that means is you might have to put in 7 plies in order to just get the effect of 6 plies out of it. So you're inefficient already. You're destroying material as you're working. It does lead to contamination, and therefore it has to have a subsequent wash. And it's a very manual process, usually done by hand, which means that also it's very human dependent between the different individuals. And then there's massive waste generation. And if we look at peel ply, which is very common within the automotive or aerospace industry, essentially very similar issues, contamination from a peel ply layer, particularly if you're using nylon-based. The reason being is water will be inducted in or induced in. The polymer fiber delamination will occur as you're pulling off. Depending on who or the human that's pulling it off and how they pull it off, they can cause delamination between this fiber and the polymer above it because of fracture toughness of the polymer. Removal is a manual process, as is already covered, and the waste is generated. However, and it's very important to point out, all of these techniques, when done right, absolutely perfectly, are very good at doing what they need to do. Prepare your surface for bonding. And then after you've done all of this, what you end up with in an ideal world is all of the handshakes agreeing. And you should end up with, if you've chosen the right adhesive for the right substrate and done the correct pre-treatment, even if it's a complicated substrate like a PEEK unit, you will end up with an ideal bond. Now, onto the reason why Xavier wants me to talk today, my commercial director. CPA is the technology we've developed. We're a spin out of University College Dublin, but this is what we are essentially selling. This technology does away with all of the previous issues that were discussed. Essentially, we've discussed the weak polymer layer, which is this material here. We've discussed contaminants getting in the way, and we've discussed the fact that the fibrous weave is the strength of a composite. If you can do exactly what the roughening and also peel ply are trying to do, but without causing any damage to the fiber structure or any potential contamination, that would be ideal. And that's what CPA does. It removes the top layer of polymeric structure, exposes the fiber system to the amount that you wish, the customer, the client. We can change that. We can trim it, skim it, fully reveal or partially reveal the fiber system. And on the top right here, you can see an example of an epoxy system where the epoxy is still present, and right beside it is exposed fibers, so previously infused. When these are exposed, you can then induce your adhesive or place in your adhesive and then subsequently bond an adherent on the other side. This could be metal, this could be glass, and it could be composite as well, it could be polymer. Whatever you want it to be. But the main point is that now what you can see across here is certainly the interface is no longer as easy to define. The adhesive will see fiber structure, and what you end up with is essentially a fiber reinforced bond joint, which is considerably tougher or stronger than the original option, which was a roughened surface or a peel ply surface. So just to explain to you what the levels of treatment can be, we've got skim, partial reveal, and full reveal. And examples of skim, applications with skim are long fibers systems, for instance, in the aerospace industry, where they would have UD or unidirectional fiber systems, and we don't want to fully expose those because they'd be flying everywhere. Whereas with partial reveal, these would be usually matte fibers, and applications for these would be the automotive industry and high-end. And then full reveal would be a similar industry as well. But the tendency is to focus in partial or skim. And to give you an idea of how the surface energy that we've discussed previously is affected by the CPA process, if you take the virgin of an epoxy system and a PEEK system, we have increased them both, the energies at the interface, by a considerable amount, up to 72 dyne, or depending on what your variation is, dyne or millinewtons per meter. And this is in both epoxy and PEEK, PEEK being traditionally an extremely difficult to bond material. So we've prepared it for bonding, and we've actually successfully managed to get it to substrate fail in a bond test. When we go to the commodity level materials, polyester, polyamides, and polycarbonates with glass fibers filled, again, you see across the board an increase in both the polar and dispersive response because of the skimming method that we use. So we don't just increase polar, we increase both. And then when you look at the future-focused materials like polypropylene with flax, we do increase the surface energy. However, we have to respect the fact that it's a biomaterial, the flax, so it doesn't have as much energy resilience as other materials. So what does this really mean in terms of the wettability envelope? Well, if we take an example of a case study that we did with one of our customers in the US, they sent us a material with this virgin envelope. So this is created from the surface free energy, not a particularly high energy, and most of it ebbed towards dispersive. They sent us exactly how to carry out their benchmark method. This is what it generated. And then they sent us their adhesive, which we evaluated and found it to be miles outside of their envelope. We weren't surprised to find out that essentially the reason why they were contacting us is because they were having reliability issues. Some days it would work, some days it wouldn't. The reason is often you will find that when the envelope is outside here, you will get sometimes good bonding, sometimes not. In the case of CPA, this was the envelope we generated for them. So essentially, we did away with the concern that they had about the reliability. This was demonstrated with real results. So we did pull-off tests internally and also did SLS testing for them. And the results, basically, you got your virgin, which of course nobody was ever going to work with. This was their benchmark material, and I would like you to note the standard deviation, which was within risk that they were happy to take at the time. And then if you look at the CPA prepared material, it is higher, and also the standard deviation is smaller, which means that now they have the opportunity to work in an operating window considerably outside of that of their original window. They could offer their customer a much better warranty and without any value change to them. And what's more, to that customer, they were more interested in, right, so you can do that benefit to us, but what will you end up causing us in the long run? So if we started this process, do we have to bond within 5 minutes? Do we have to bond within 2 hours? How long? But so the answer, when we carried out evaluations, was that 7 days later, we were still at a very similar number to what they required. Essentially, we started out at 72 or 73 dyne. We finished up at 68 dyne. It was still above the requirement that they had had. And for completeness, and for you to be all to be able to see, I also demonstrated where the dispersive was. So the dispersive plateaued and remained, and this is what's called polar restoration. Essentially, the polar energy was being satiated by some of the presence of moisture in the air. So after 7 days, in an uncontrolled environment, that is on a shelf in our lab, that was the results. We have demonstrated that to 22 days for epoxy carbon fiber. So the outcome, essentially, when you carried out these tests, and they're long-term tests, and you carry out in maybe 22 days, some of our tests have been carried out months afterwards. The main outcome, which everybody is really interested in, or most people are interested in, is the SLS testing. I have DCB data as well, if necessary, but it's a bit complicated to explain it. But the epoxy to CF, where you're matching hand sanding. So no surprise, we cause substrate failure. Hand sanding already does that. You can't do any better than what you already achieve. But when it comes to peak CF, we outperform hand sanding presently. And when it comes to PPS and PEI and PIC to an alternative material, which is a very interesting area, these we outperform again, the alternative benchmark or braiding. But when it came to PIC to aluminium, it was the first time that the failure occurred on the aluminium side. They'd never anodized the aluminium side during testing because they'd never had to see it cause a failure. It now failed on the aluminium side. The PIC held longer than the aluminium. And then the final one, which is PPS carbon fiber to epoxy, which is an interesting area because it's an overmold. Essentially, the PPS was treated, and then the epoxy was cured onto the surface of the PPS. So we exposed the fiber structure, and then they cured the epoxy onto that surface. It caused substrate failure of substrate failure of the epoxy, the consolidated epoxy afterwards, and reached the maximum interlaminar shear of the epoxy. Target markets that we're interested in and people we'd like to talk to: the automotive, space, drones, aerospace, and sports and equipment. The reason being is we've seen a benefit in all of these markets, and a lot of the materials that are applied within these markets are interchangeable. So data that we have generated for instance, the sports equipment is actually relevant to both automotive, space, and aerospace. So these are the key areas or target markets for us. So just to finish it off with an understanding of what we sell, this is what we sell. It's a control unit. It's a VPN-based control device. We are looking to move to a cloud-based device in the coming 2 years. But the main thing that we sell is this component. It is attached to a plasma generator. This is a partner generator from Axis, who are based here in France. We plug our controller into the back of their unit. It takes it over, and then when it's installed in your facility, it will allow the plasma emitters, which are also designed specifically for PlasmaBound's approach or technology. It enables a more reliable treatment with less capital, personnel, and also process steps. To give you an overview of the other benefits that are considerable but important to us as PlasmaBound, PlasmaBound's CPA solution reduces the solvents and primers, chemical waste, wasteful pre-treatment processes, VOC emissions, and importantly, the energy consumption that is used in preparation of materials. Transport complexity, because now you can transport them as you want. We've seen 7 to 22 day lifetime of our treatment, which means that you can prepare it anywhere in the world and use cheap or green transport relative to flying it in or any of these other methods that are used. And then part rejections are reduced because we are a more dependable method. So, in summary, poor adhesion or unreliable bonding can result in costly recalls. Traditional preparation methods are not future-focused, as in they're not sustainable. Interfacial properties play a key role in joint performance, and PlasmaBound's CPA solution provides a unique opportunity to improve joint performance and reliability in a sustainable and cost-effective way. Thank you for your time. And as I mentioned, Xavier Montebert and Abhilasha Tumar. Abhi is there, Zav is down there. If you wish to discuss this any further, please discuss it with them. And also, we are in, I wrote it down because I didn't have it in the presentation. We are in Hall 5, N80. Isn't it? N80? Yes. Got that one right. All right. Any questions? No time for questions. Sorry, guys.